A reminder that we're searching for advisors and research managers. So if you're aware of somebody who might be suitable for that, then please let us know. And again, reminder that we would like to figure out some way to collaborate closely together, put together some projects for the next few weeks in order to try to solve some of the pressing issues and questions that we have been discussing during this whole week. And I would also like to take a moment before we start to remind everyone to please respect the privacy of our speakers and participants. Some speakers have requested that they not be recorded, and we do hope that everyone will honor and respect that request. So with that, I will hand it over to Tomas. Thank you, Tomas, for coming. Actually, also having a chance to be here locally, and we're very much looking forward to your talk. So over to you.
Thanks for the introduction. So we'll be talking about some sort of like growth of complexity in some artificial mathematical systems. Otherwise, I'm Tomas Mikolov. I'm currently at CIIRC here in Prague, where I'm starting a research group on this artificial intelligence with like this long-term ambition of achieving, like, say, some sort of human-level intelligence in the future. So I'm having a couple of students working on various topics, and I will present the works that we published this year and last year on this topic of growing complexity. So what can you actually think of it? Like, what does it mean? What could it be good for? Like, what is the complexity? It's like intuitively we can say that we can see complex structures all around us, like in the world, in the universe, and all this is somehow like emerging from some simple behaviors that are iterated over time. Like if you look at the universe from some like large scale, it seems kind of like some dust just moving, like the galaxies and everything. And it's kind of like funny to realize that the universe that we are living in is able to create a lot of things that intuitively to us look complex, like say intelligence, us like humans, and so on. The question is, where does this complexity come from? This intuition is nice, but can we actually say something more like mathematical about it? Can we design some artificial systems that can behave kind of like our universe, like create, you know, like a level of complexity, or like artificial universes where artificial life can be started, or even like artificial intelligence can emerge? It's kind of like, in my opinion, like interesting questions. It's actually not that easy to actually answer them. I wouldn't say that we did answer them fully, but at least we have some insights that I will talk about in this presentation. So again, like I think that if we care about strong AI, then this topic of artificial evolution can be like very interesting, because if you consider, for example, like a system that can reach arbitrary complexity, then I think this open-endedness of evolution is like very, very interesting topic. Like we would like to set a system that doesn't have any upper bound, something that can go on forever and create new and new structures like indefinitely. So that's for the motivation. But if you actually start looking at some simple mathematical objects and try to say which ones are more simple, which ones are more complex, where there is some emergence of structures, like intuitively, again, like we can look at these pictures. There are just some checkerboard on the left, the Sierpinski triangle in the middle, and then some subset of the Mandelbrot fractal on the right. And intuitively, I think that like we can say that the checkerboard is the simplest one, because it's kind of like boring. You don't really see any patterns emerging there. It's boring. You can make the checkerboard like many times bigger, but it's going to be still the same thing. There's not going to be anything new ever. With the Sierpinski triangle, you can see that there's actually like something more interesting happening, but it's still boring in the sense it's very regular, and you can always say, oh, it will be like millions times bigger. While when it comes to the fractals, like that Mandelbrot set, it's looking quite a bit more complex, even if it's based on like some very short mathematical equation. And I think that's like a very interesting thing, that even if these objects from the maths perspective are kind of like the same complex from some point of view, from our point of view, from the human point of view, there's definitely much more complexity arising in the fractals. So how would we go about it? If we want to measure this in some formal way, well, the simplest idea can be to use minimum description length, also known as Kolmogorov complexity, which would be the length of the shortest program that generates the pattern that we are interested in is basically this minimum description length, and complex patterns should probably have a large Kolmogorov complexity, and simple patterns should have shorter description length. Well, it's formal, it's well known. Many people actually like this concept, but it actually has a lot of problems. Like first one, it's not very computable. There's like some long proofs, so it can be explained, but in a simple way, if we are given a description of a string that we believe is the shortest one, it's impossible to prove that there are shorter ones that will not, shorter descriptions that will produce the string, because there are like programs that are very short, but that will never halt. So we can't actually prove that the programs will not halt. That's the halting problem. So for this reason, it's actually not computable. We can't actually say that some description length is minimal of some pattern. So we can make just some approximations, but they have all kinds of problems. For example, we can take data compression algorithms, and I could show by examples that actually they can fail. Like this approach can fail like totally. Then there's also like this choice of computational model, because it's assumed from the Kolmogorov complexity point of view that the computational model that we are using is Turing complete, but there are many Turing complete models, and there's a lot of bias. For example, if you have a programming language where you have a single instruction that generates the whole pattern that you are interested in, then the description length will be always just this one. You just need to output this function, and basically you hide all this complexity in that description that Turing machine or in that programming language that you are using. And the other issue is that the Kolmogorov complexity is maximal for random strings. Like if you have the most disordered strings, then they will have the largest complexity. That's actually not what we as humans would consider complex, as I will show later in examples. Like you can think of white noise. Does it look complex to us? I would say not really. There's no structure. There's nothing really happening. It's kind of like the checkerboard here, just it's completely random. So I would say that's actually not the best way how to approach complexity. We can use some information-theoretic approach based on, say, Claude Shannon's work from the last century. It again sounds very cool and very mathematical, but we can't actually measure the information like in a gain or like there's no increase of information in these complex systems, which is kind of like funny. You may even wonder if the universe was deterministic, if there would be any growth of information in the universe. And from the information theory point of view, no, it would be still like basically constant. You just need the starting state. And then if you know the number of time steps you want to go forward in time, then you can simulate the whole thing deterministically. So there's actually no information being created. There's no randomness. And for that reason, there's no information. So again, like information theory does give us results that don't really like match our intuition. So we can think of other approaches. Actually, I did read part of a book called Quark and the Jaguar from some physicist who did think of a lot of actually Mary Gell-Mann for those who know physics, but who did think about like a lot of complementary ideas how to define complexity in the universe and in physics and so on. And one of them, for example, that we can think of the time that is needed to compute the string or the structure, that it can be actually the complexity metric, like the complicated patterns will require a lot of time to be computed. It's kind of like the intuition behind it. Or maybe we can define the metric by the number of identifiable patterns that will actually like kind of solve the problem with the white noise. As I said before, that the white noise would have like very large complexity from the Kolmogorov complexity point of view. So in this case, we will rather think of like how many patterns we can describe. Like again, if I would show the pictures, then you can say on the checkerboard, you have like very small number of identifiable patterns. You can just say that there's like these black and white squares that are just repeating, and that's all. And so you can actually describe the whole thing completely with a short description. If there would be there was white noise, then there's actually no patterns that you can talk about. So again, the description length would be, or the number of patterns, the length of this list would be kind of short. While when it comes to this Mandelbrot set, you can see that you can talk about like the structure. You can say, oh, there's some circle and some dots going into the center and whatever. And suddenly, actually, this seems to be more meaningful and does correlate better with our intuition that this length of the list of these identifiable patterns can be actually like a good complexity metric. So that was all described in that book that I mentioned. But of course, if you want to actually do it, there's a question like, what do you actually choose as this space of all these artificial universes that you will be considering? Well, with my students, we think at first of like Cellular Automata, because they are pretty much like as simple as it gets when it comes to computational systems. That at the same time, at least some of them are Turing complete, so they can actually represent an algorithm. So just to explain very quickly, the Cellular Automaton is like a kind of like you can see it as a parallel computation model where you have a, say, just a tape in the 1D case, where actually on this picture on the bottom you have like the time axis is going from up to the down, and you can see that there is this iterative computation that is happening on the whole tape, where the state of cell in the next time step, which is like one row to the down, is computed based on the state of this cell and its neighborhood in the basically previous time step. And then there is this lookup table that is shown above that is basically saying how this computation is performed. So it's like very simple, and at the same time it can be quite a powerful computational model. So it was studied by Stephen Wolfram, who did intuitively define like 4 classes of behavior of these elementary, simple, one-dimensional sort of automata. Well, the first class is shown here, like on the top left, where you can see that the computation kind of stops very quickly. There's after a few time steps, I think like 5, there's nothing more going on. Basically, the whole memory is like full of zeros, and there's nothing interesting. That's the class 1. Kind of like converges quickly to some stable state, and nothing more happens. Then there's the class 2 shown on the top right, which is like some periodic behavior. So still nothing interesting really happens. Computation goes on like forever in some like very basic repeating pattern, and nothing really like special about it. Then on the bottom right, you have the chaotic behavior, where you can see that there's not really like any structures emerging. You have something that looks a little bit like this white noise, basically a lot of like random things, and we don't really see much any order. And then the class that was considered the most interesting is on the bottom left, which is actually the interesting class that's somewhere between the chaos and the regularity. There are actually some computation that seems to be non-trivial, seems to be happening, and also like goes on for some reasonable number of time steps. So if you would think of like of all computational universes, then this is like the simplest step forward, and then we can believe that our universe is actually not on the based on the first 3 types, because then we would not really see any structure around us, but it's more like of the type that is shown on the bottom left. So this was done actually manually by Stephen Wolfram, who did basically just look at these time diagrams of these automata, and he decided, like based on his intuition, what he thinks seems to be looking like complex and interesting, and which systems are either chaotic or boring. And of course, like there's this example that people did like these automata quite a bit in the history, and they developed like this one example with a 2D automata where you don't have just the tape, you have a grid, and then you can see that as the simulation goes on, you have some sort of like emergence of patterns, like some behavior happening, and again, like some people see it as like a possible way how to simulate the whole universe, like just having some giant sort of automaton. So what we actually did, because as I said, like many of these ideas that I discussed before are based on intuition, and something that is kind of like informal and you can't really compute it. We were thinking with my students, how can we actually develop something more formal, something that will be based on math and something that can be actually computed and not just something like Kolmogorov complexity, which is like a nice concept, but we can't really go very far with it. So one of the ideas was to use the average transient length, where this is basically the number of time steps that it takes for the automaton to get into periodic behavior, because all these automata, when they have fixed size of the tape, they will start repeating the computation at some point, because there's just fixed number of combinations that the tape can represent, which is basically 2 to the power of n, when n is the size of the tape for the automaton. Then there are just 2 states in each cell. So we computed this average time that it takes before the computation basically enters a loop, and then we just we did look at how this transient length grows as you are increasing the size of the tape, and it actually gave us like pretty good classification and can be computed surprisingly well. I mean, like for most of the automata, it converges to like a good classification quite quickly. And we did obtain these classes actually using this approach. There's this bounded class, which is looking like very much like the first 2 classes from Wolfram's classification, as I was mentioning, which is basically the boring one. That's basically when the transient length is very short and doesn't seem to be increasing with the grid size. So basically, these automata are very likely to go into some very boring state very quickly. And there was the logarithmic class. Where the transient length keeps somewhat increasing, but very slowly. And again, that seems to be kind of like boring. Actually, it's like the largest fraction of the elementary cellular automata are of this type, that they just don't really do much anything interesting in the longer term. From our point of view, like from the complexity point of view, the linear class or later polynomial class is actually the most interesting, because the automata where the transient length grows kind of like linearly with the grid size seems to be producing this complex behavior that I was talking about. And then there's the final class, which is the exponential one, which is corresponding to the chaotic systems that do not really seem to be creating any structures. Then there doesn't seem to be any emergence of interesting things. And there are like 2 more classes that we discussed in the paper, which were like represented by just a few automatons. So I will skip that, but you can check basically this paper that we published just last month at this Artificial Life conference. So for the conclusion, like in this paper, we have developed a formal approach for identifying complex systems, and the automata where the average transient growth grows like linearly or polynomially basically seem to be the most interesting ones. So basically this means that you can have an automaton. It doesn't have to be just elementary automaton. It can be 2D or 3D. I will show actually examples at the end of the talk, but it can be pretty much anything. And then you compute how long does it take before the automaton enters some sort of loop, like basically when the computation stops. And based on this, you can classify the behavior quite well. There was also like other idea that we published actually last year at this symposium on artificial life, and that's using the compression-based approach. As I was mentioning that idea from that work and the Jaguar book before, then we actually did think of using compression for like estimating how many patterns are like identifiable in the system. It's actually not that easy in the sense that if you just build a compressor of these cellular automata, then the largest compression length will of course go again to the chaotic automata, basically the most disordered ones, because they are the hardest to compress. So what we actually did as extension of this idea of using data compression was to have the requirement that the compressor should work well over longer time scales. So if you, for example, train the neural network compressor at time t, then it should work kind of well, even like say FT plus 500 or something of this sort. So we had this constant, and we tried to basically enforce that the metric corresponds to the patterns that can be that have to be basically described by this compressor, but also like these patterns should be stable in time, so that if there's some emergence of patterns, that these patterns at least partially should be present even in the future, so that the system basically does not create complexity too quickly in the sense that it will just get destroyed right away. And here are some examples, like what automata we could find automatically, like in this 2D case, because the number of the like these possible computational universes is like huge. It's like a extremely large number, like of just these automata that we can construct. So we did just randomly sample these automata, and then we did use this complexity metric to pick the ones that have the highest emerging complexity. And here are just the examples. As I said, like you can see there are sort of like gliders, and the behavior basically seems to be like what we are looking for, kind of like artificial life-like. And then back to that other paper that I was mentioning in like in the beginning, where we were using the transient length. It was looking at like similar in the sense that when we tried it on the 2D case with these like say 2 or 3 state automata, and this was the log class where basically the complexity seems to be, the transient length is increasing kind of slowly with the grid size, and the complexity doesn't seem to be very high. Then there was the linear class, as I said, like that was the interesting one, when there already like seems to be like some structures appearing. Then the polynomial one, which means say quadratic or cubic growth of the transient lengths, and that seems even maybe more interesting than the linear one. Like there's quite a bit of structures that seem to be rising in the automata that belong to this class. And then of course there was the final one, which is the kind of like exponential class, where the complexity is increasing so quickly that basically nothing really survives, and it really looks like some sort of like white noise. And we intuitively believe that these chaotic automata are not good ones to represent this artificial life or artificial intelligence, but we don't have any proof for it. Like it's just what we are thinking at the moment. That it would be great if we can actually prove it, but that's like future work. And of course, like you can add more states and again do this classification. And actually, with more states, things are looking even more interesting. Like you can see that there's all kinds of different behavior that we could observe that seems to be like non-trivial. And we think that this can be kind of like the basis of this growing complexity, basically like artificial computational universes that would have interesting properties that we want in AI. So for the conclusion, we did develop these different ways how to measure growth of complexity in these artificial computational systems. And we believe that this can be kind of like a basis of this open-ended evolution, like a system that keeps generating new patterns forever, and that is getting more complicated, and that if it would have enough resources, then there should be possibility that it can generate pretty much anything, including say artificial life with intelligence and memory and all these things being basically emergent properties. Of course, like we didn't really prove that what I was showing, that it's really open-ended in the sense that you may believe that if you would, for example, scale some of these systems that I was showing to some much larger sizes, maybe there's actually some cap, maybe there's some boundary that the complexity would stop increasing at some point. We don't really know. That's of course like a open question still for us. If these systems would be much larger, can we actually observe some new type of emergent behavior that we couldn't observe actually in the small scale system? So that's actually one of the projects that's currently going on, and I'm curious about what results can we achieve. So we don't really have any proof that these systems are open-ended, but we believe that they may be. So thanks. That's basically the conclusion of my talk.